My force due to the bicep then is 6 divided by 9, which is 2/3 or 0.7 pounds. No, that's not right. No, I'm sorry, guys. I made a mistake here. Y'all see what my mistake is?
Well, I guess that's supposed to be 7.
7.
Well, 7 inches or
No, let me show you. I'm sorry, guys. I'm going to have to erase all this.
You're still tired.
What's that?
You're still tired.
Okay, so our 3 pounds is not applied at 2 inches. It's actually applied at 9 inches. Right, this is our 3-pound force applied at 9 inches, and our force due to the bicep is applied at 2 inches. You'll follow that? So our torque due to the forearm has a weight of 3 pounds. So if I have it like this, there's a weight pulling down of 3 pounds, and that weight is applied 9 inches from my elbow, 9 inches from the axis of rotation. The bicep is right here, attached right here, is pulling up on my forearm, and it's about 2 inches from the axis of rotation. All right, so 3 times 9 is 27. Is equal to the force bicep times 2 inches. I divide that through by 2, and then I get the force due to the bicep is equal to 27 divided by 2, which is 13. We'll just call it 14 pounds. All right, so to lift this 3-pound forearm, you have to actually apply 14 pounds of force. Okay? That's the point there, that your lever, what class of lever is this? 1, 2, or 3? It's a 3rd class lever, right? Very inefficient, that you have to apply a large force to move a small force in response to a small force. This is a class 3 lever. In the body, yeah. Which means that your muscles have to apply large forces to affect small forces. All right, so what happens if we add a weight to this? So I'm gonna draw another diagram of our forearm. I'm gonna make it a little simpler. This is our forearm right here. Let's say that we add a 5-kilogram mass. 5 kilograms is about 10 pounds. So I'm going to add a 10-pound mass down here. All right. This distance, halfway was 9 inches. This is going to be 18 inches. I also have a 3-pound weight right here. And so this distance is 9 inches. And then I want to know what is the force due to the bicep that will hold it up. That force is right here, and it's at about 2 inches. And so here I have 3 different forces that are at work. I have the weight of the forearm. It's applied right here. It's pulling my forearm down. I have the dumbbell that I'm holding. That's about 10 pounds. It's likewise pulling it down. And then I have this force that's attached to my bone that's pulling it up. That's a couple inches from the axis of rotation. I would do something very similar here. I compare my clockwise and my counterclockwise torques. So I would say 10 pounds times 18 inches plus 3 times 9 inches is equal to the force of the bicep times 2 inches. So it's going to be 180 plus 27 equals 2, the force of the bicep. That's 207 divided by 2. and that's equal to, well, about 104 pounds. So your bicep to lift this 10-pound dumbbell, right? A 10-pound dumbbell, not that heavy, right? It's pretty easy. Everybody, I think everybody here can lift a 10-pound dumbbell, but it requires more than 100 pounds of force in order to lift a 10-pound dumbbell. And doesn't that seem like a lot? But it's the fact that we have this third-class lever. A third-class lever is very inefficient, especially in the bicep, because you have such a small moment arm here. But really you want your bicep to sort of come out of your arm and attach like right here, so that you get a much longer moment arm. But then it would look kind of funky. I don't know what that would look like. Okay? Be able to work these types of problems. I'll give you numbers that work out very easily, that are even easier than these. Factors of 10, 2, they'll be very simple numbers to work with. But make sure that you can work through these types of equations, being able to solve these types of equations. I know that seems like gobbledygook for some of you. And please come see me if that's the case. I can sit down with you and help you. But practice will help too, going back through those old exams and making sure that you can work those problems. You can do it. I know that you can, even if it seems like a jumble of letters right now. But with practice, you can get it. You need to get it by next Tuesday when we have our exam. Okay? All right. Let's see. Let's do this other one, and then I'll do a clicker question for y'all to try this out. As I said, you won't have to do this type of problem, but I do want you to understand the way the deltoid works and why the deltoid is such a large muscle. That we talked about this before class, but that it's because of that angle is so shallow. Okay?
You can just do that.
We talked about it, but we're going to actually do the math here.
I thought that was about 10 pounds.
No, we were looking at your bicep holding up a 10-pound dumbbell. Now we're going to look at the deltoid holding up a 10-pound dumbbell. Okay?
I was doing the second part of the first question.
Yeah, I was doing the second part of the first question. Yeah, what is the force when holding a 5-kilogram mass? I think are you still waking up, or was I unclear?
Yeah, very.
A little bit of both, maybe. Okay. All right, so consider this lateral raise with a 10-pound dumbbell. I want you to estimate the force exerted by the deltoid in order to hold up the weight of the arm. So a couple things here. Want to look at what is the force due to the arm, and then also what is the force due to the weight, and what force do those exert, and then what force does our deltoid have to exert in order to do that lateral raise, where you lift the arm up like that. So I'm going to draw a schematic of our arm. This is our arm. It is it's like this. So this is my axis of rotation, and it's going like this. I have three forces that are acting on the arm. What are they? What are the three forces that I have acting in this situation? The dumbbell, right, which is 5 kilograms by 10-pound dumbbell. The weight of your arm. And we will always assume that the weight of an object will be exerted at the center of the object. We call that the center of mass. So the weight of the arm is going to be right about in the middle of the arm. Unless, of course, like you have huge biceps and little bitty forearms, then your center of mass would be like right up here. All right, and then what's the third force? We have the weight of the arm, the weight of the dumbbell, the deltoid. And what were you going to say? There's no normal force in this case. I mean, there is a normal force within your arm when you have the objects that are bumping up against one another, the bones. But no normal force here. So, the weight of the arm, I'll call that F arm. We have the weight of the dumbbell, I'll call this FDB. And the dumbbell is about 10 pounds. I'm going to do it in newtons. So the mass, 10 pounds, is about 5 kilograms. So I'm going to say that this is 50 newtons. Do you know how I went from 5 kilograms to 50 newtons? I said that the weight is equal to m times g. So 5 kilograms times 10 meters per second squared, that's equal to 50. Anytime I give you a mass, to find the weight, you take that mass times 10. In the book, they use 9.8, but we use 10 just because the number is easier to use. The weight of the arm, we'll say that the arm has a mass of about 10 kilograms. So the weight of the arm is what? 100 newtons, right, 100 newtons. That might be a little heavy, but it's a big arm, big guy's arm. And then we have the deltoid, which is applied at about 10 centimeters. That force, as we said earlier, is very shallow. We'll say that this angle is about 5 degrees. I'll call this FD, the force of the deltoid. Now we also need to estimate the distances for the center of mass of the arm. Center of your arm is right about here. That's measured 10, 20, 30 centimeters. So right about 30 centimeters is the center of the arm, and about 70 centimeters down, or 60 centimeters down to the end. So about 30 centimeters. And then down here, actually I wrote 70, so I'm going to do 70 centimeters here. It really is about 70 centimeters. Down to the end of my finger. You know, see that? 70 centimeters. No, y'all can't see it in the back, but it's true. But the center of mass of the arm is a little bit shy of 40 centimeters. It's right about here, at about 30 centimeters. Just because you have more mass in the arm here. You follow what I'm saying? Yes. Okay. All right. So now I balance my torques. I have the 50 newtons times 70 centimeters plus 100 newtons times 30 centimeters, and then that's equal to the force of the deltoid times 10 centimeters times the sine of 5 degrees. As I told you, you won't have to do any trig functions on your test or on the reading quiz, but I just want to show you here how big the deltoid force has to be, how big it works out to be because of the sine. So I'm just going to give you the answer here. The deltoid works out to be 7,500 newtons. So a person has a weight of about 700 newtons. To lift a 10-pound dumbbell requires about 10 times the weight of a person, the force that's applied by your deltoid. That's something, isn't it? That the deltoid applies such a large force, and that's why the deltoid is one of your bigger muscles in your body, because causing this motion is difficult. What happens to the angle? Oh no, never mind. Don't worry about that. All right. Let's do a couple of clicker questions in the back. See if we can find some torque questions. They ought to work. Looks like we've done some of them. Let's try number 32 here. While you are doing number 32, I'm going to look at some of the other old exams. Which one is this? Is this spring 16 that you have in your book?
Yeah.
Okay. Y'all go ahead and do number 32. I'm going to pull up another question. It's exam 1, number 32. It's back at the back. No, not page 4.
It's technically page 113.
Okay. But there's no page numbers on it.
Or that is nice. Example.
Number 32. So go ahead and work number 32. it's not up here. It's in your book. I'll show you. I got it. Number 32. We'll stop in just a few seconds. Stop at 204. 204. All right, awesome. B is right. Did y'all hear about the guy? He was in this terrible accident, and he lost like his left arm and basically his entire left side of his body. You hear about that? He's all right now. All right, number 32 is more than 20 pounds. That because it's a class 3 lever, it requires more than 20 pounds to hold it up. Oh, let's see what else we got. Have we done some of these others? Yeah. Did we do 29? We've done a lot of these, haven't we?
The only one we haven't done, I think, is 27.
All right, let's do 27. For 27. All right, let's stop at 110. 110. Y'all are overthinking this a little bit much. 110, I'll stop. All right, this sort of gets back to something that we said last time. It was in your book about tension. So when I have a forced tension that's acting in a rope or a cable or a muscle in this case, that the tension that's applied at one point is felt all the way throughout that object. So remember we did this, I think Vanessa pulled on this with 5 newtons, and I felt 5 newtons at this end. So here, if I apply 100 newtons, then the force at the insertion point and at the point of origin is also going to be 100 newtons. So B is the right answer here. Let's go back to our notes. We had some other torque problems back in our notes. So go back to your chapter 2, page 13, I think. Let's go over this first, though. So a couple of things. The Erector Spinae, is that how you say that? Is that how you say it? The Erector Spinae. These are the muscles that help you to stand up straight and to bend over. There's a picture of like an old man in your book where you just see the picture where he's bent over like that. You see the old man in the book? That was the model for that diagram. But in a similar way for the deltoid, because the angle is really shallow, there's a lot of force that's going on to make your body go up and down. And plus, the trunk of your body is pretty heavy. Like, it's one of the biggest parts of your body. And so there's immense forces that are exerted by those muscles. Talked a little bit about balance and center of mass, but the center of mass is a point in the body where all the mass is located. I'm going to put that in quotes because, you know, all the mass isn't really located in that point, but we think of it as being located there. So, like, for example, with this meter stick, the mass is distributed from one end all the way to the other. But when we talk about the center of a mass, that's a point within the object where we imagine that all of the mass is located. Where if we were to imagine the force weight of this object, then that force weight would be applied at that point. And the center of mass for a meter stick is where exactly?
The middle.
In the very middle. And the reason it's at the very middle is because, well, it's a
Symmetrical object.
it's a symmetrical object. It's the same throughout. You can find this is kind of cool, you can do this with any object, whether it's regular or not, by putting your fingers like this, and then you can move them, and they will always meet at the center of mass. It has to do with the friction and the normal forces that are being applied, that they will compensate for one another, always at the center of mass.
I use that at work a lot.
A meter stick?
Well, not just like the center of mass thing, because I'm always lifting.
For lifting big trays. Right. And if you're
balance it.
Yeah, if your tray is not balanced, if you're not at the center of mass, then you'll tip over like that.
It's in my case.
Yeah. But I used to wait tables, and the general manager would always say that we would take the plates out of our check. But they do that to you?
No.
They never did that to us either. They're expensive
We
plates,
joke
those
about
kind
it.
of plates. Huh?
They'll joke about it, especially if it becomes excessive, but, no.
Yeah. Now, what if our center of mass, or if our object is not symmetrical? Like, say, for example, if I have something like this attached to the end, then where is my center of mass now? It was at 50, but where is it now?
It'd be slightly closer to the,
Right, it would be somewhere over here, the center of mass. But you can do the same like we were doing earlier. Let's try it. We'll figure out where exactly that center of mass is. It's right about there. So right at about 57 centimeters or so. All right, so that's the center of mass. What about these objects? Where is the center of mass for each of these? Just take a moment and just mark them where you think the center of mass is. You're looking at it like it's right in front of you. So there's the triangle, the arrow, like as if it were a meter stick. But where would the center of mass be? All right, so with the triangle, it's going to be where? Is it going to be right in the middle of the triangle? Well, this one isn't an equilateral triangle. This is an isosceles triangle. And the two legs are a little bit longer. So our center of mass is actually going to be a little bit down towards the bottom, where more of the mass is located. How about this? This is a lot like our meter stick, this arrow. Our center of mass right in the middle? No, it's going to be to the left or right of that? To the right. So it's going to be right about here. So for the arrow, because I have more mass on the end, the center of mass will be right about here. Now on the test, I might give you a shape. I can give you several selections on that shape and ask you which is the center of mass. What about this one? Center of mass. Whereabouts? In the middle? Yeah. And the center of mass on this one is right about here. It's true. That's not the middle. The center of mass doesn't have to be within the body or within the object. And that's why, for example, when you're that old man, you bend over like this, your center of mass went from being right here to when you bend over, your center of mass is like somewhere over here, which can cause you to be off balance. Your center of mass doesn't have to be within the object. It can be outside the object. Taylor? Because the center of mass, it's not a physical point, right? It's a place where we imagine, mathematically, it has to do with the distance to all the individual masses that make up an object. And so you would break up your body, your object, into a bunch of little bitty mass pieces, right? And then the center of mass would be, like for example here, would be a result of the product of the distance to those little point masses and the actual mass of those point masses.
So how can you tell if it's not in the
Well, up here, if we were to say it's right here, oh shoot, no. I'm going to bring you something. I'll show you. When we start these questions, I'll bring you something. I think it'll illustrate it better. Okay?
I have an idea. Is it because it's a circle?
Yeah, you can think of it as a circle. That's a great way to think about it. Although this is a semicircle.
It's like a half circle, but if you put the whole thing around, it would go in the middle.
Right. So yeah, great idea. So if I have a donut, the center of mass for the donut is right there in the hole. Okay? But that's something when I start this question, I'll come and show it to you. All right. So in order for a person to be well balanced, their center of mass should be, where should their center of mass be? Where? No, in order for them to be well balanced, it needs to be over their feet. Right. So if I want to be as balanced as possible, I want my center of mass to be centered directly over my feet. And then if I am off balance, I can be off balance in a bunch of different ways. I can hold like a heavy package, or I can, have a baby or whatever, and then that puts me off balance because my center of mass moves out from over my feet, which is why you see pregnant women like this, right? I can bend over. That makes me to be more off balance because it moves the center of mass from over my feet to outside of my body. I can move my leg. So if I take my leg and move it out, that moves my center of mass.
You can put on a little bit of weight, would you say that?
Yeah, so yeah, if you have extra weight that's in front of you, then that makes your center of mass go away. All right, I want y'all to try something. Let's see if I can. I want you to find a wall, so you'll stand up. Find a wall that you can stand up next to flush. So this wall works well for that. That wall back there also works well for that. So find a wall that you can stand up next to flush. I want you to put your foot up next to the wall. You'll see how I'm going? Now right now your center of mass is over the wall, or right over your feet, right? You should have your shoulder up next to the wall, and then you should also have your foot right up next to the wall. So now, you do something really simple. We're just going to take your foot, whatever foot's not up against the wall, and just lift it out. Take your foot and just go like this. Go ahead. Go ahead. Let's see. Come on, Kristen. Come on, Caitlin. Now you have to keep your foot up next to the wall. Lift your leg up like this. You have to lift it up off the ground. No, Caitlin, go away from the wall. Who's got it? Sarah, did you get it? No, you can't do it, because when you do that, if I'm standing not against the wall, I just shift over. I lift my leg up and I shift the rest of my body over, and that causes my center of mass to still be here. But when you're up against the wall, you can't do that because your center of mass moves out away from your body, and you just don't have the right set of muscles over here to keep everything lifted up. Okay? It seems like it should be easy, but it's actually quite difficult. Y'all can have a seat. So ways to a person can be off balance. A couple of different ways. You can have a person that's carrying a large object in front of them. You can have a person that is and a large object with child or a box or whatever it is. You can have a person that's lifted one of their appendages up, their leg, and puts them off balance. Or you can have, like the old man in the book, you can have somebody that's bent over, and then that puts their center of mass all in places that are outside of their body, away from their feet. So, right about here, right about here, right about here. Their centers of mass are all not over their feet. They're out off balance. Okay? This last little section isn't in your book, but this is a project that we did a couple of years ago with some students, where there are these models. These people developed a model for walking, and this was a model that's given by the leg length and the stride length. So this is the stride length, and then this is the leg length. And how they came up with this model, they said that your speed of walking, everybody sort of has a normal speed that they walk. Your speed of walking is dependent upon the stride that you take. Normal people probably take a little less than a meter stride, and the lengths of your leg, which is going to be the square root of the length of your leg. And then those two factors combined, your stride length and your leg length, you can predict what's going to be their typical walking speed. And so we did this in my class like last year, I think. We're not going to do it this year, but last year had everybody walk. We measured their speed and then plotted this walking speed versus the stride leg length. And notice that that V is directly proportional to that D over L. So as D over L, or D over square root of L, increases, then we should see an increase in our walking speed. And that's what we saw. I mean, there's some scatter there, but we certainly see that as you increase the stride length and as you increase the leg length, that your walking speed adapts according to this model. And this model is based, it sort of treats the leg as a pendulum. We'll talk about pendulums later. And develops this theory about what should our walking speed be. I just want you to see that science is a predictive thing, that we can take very simple models and predict what the physical world is going to be like, or in this case, the human performance world. All right, let's see. I have a few clicker questions I want y'all to try. Let's try this first one. I'm going to run to my office while y'all do this one. I'll be right back. You're doing this one right here, and I'll be right back. Folks, just a few more seconds. If you finish this one, go on and do the others. I'll stop at 1:15, okay? 1:15. Okay, I think D is the right answer. Yeah. So here, we're just looking for the net force, right? So if I have 20 newtons to the right and 10 newtons to the left, the net force, that's the sum of the forces, is going to be 20 minus 10, or 10 newtons. And because it's positive, it comes out as 10 newtons to the right. How'd you do it?
Kilograms?
Uh-huh.
I realized the net force has to be 10 kilograms, and then I just use the one
No.
that's higher.
Yeah, no, that's not correct. So the 10 kilograms, you don't really need it all in this case. It doesn't matter. It could be a 2 kilogram mass. It doesn't matter what it is. So you look at your force to the right, force to the left, and you take the difference in those. Remember, to the right is positive, to the left is negative, doing net forces. What's the acceleration of this object, or that 10 kilogram object?
About 10 meters per second squared.
No. Well, our force is what?
1 meter per second squared.
It's 1 meter per second squared. What is our force? It's right there. 10 newtons. We have a mass of 10 kilograms. And so my acceleration, I can find from Newton's second law, that's F equals ma. So A is equal to F over m. That's 10 newtons. Now here the mass is important. Over 10 kilograms, that's 1 meter per second squared. Okay? Let's try this one on the right. It's identification. All right, let's do a few more seconds. Let's stop at 23. 23. Awesome. Very good. D is right. That's called your insertion. Remember, origin is up here, doesn't move. It's like where the force originates, if you want to think of it that way. And then the insertion, where is that muscle inserted onto the muscle? The insertion point is the part that moves. So D is the right answer there. What about this one? The force due to the muscles. What muscles are these that cause them to do this motion, first of all? No, not the deltoid. These are the muscles that cause us to bend over and stand up straight.
The erector spinae.
Yeah.
Whatever.
Spinae? Is that right? I don't know. Okay. Anybody know? All right. What are those? What is the torque caused by the erector spinae muscles? That's Fm. Go clockwise and counterclockwise, or is there no torque at all? All right, let's stop in 5 seconds. Good. A is right. It's a clockwise torque. So this force right here causes a torque that's in that direction. These other forces cause torques that are in this direction. Right, so if it was balanced, I would set those two torques equal to one another, like we've done, say, with the seesaw and some of the other problems. Remember the erector spinae, they have to apply large forces because this angle is really small. And while you won't have to calculate that angle or use your calculator, I will ask you questions about that regarding that muscle and the deltoid muscle. All right. Answer this one about the erector spinae. Yeah. It's okay. Look around on the test. Sometimes you might have a question that you don't know the answer to. But if you look in some of the other questions, it might give you a hint or jog your memory. Let's stop at 27. Good. B is right to stand up straight. Lift heavy objects. Well, you can use your erector spinae muscles to lift heavy objects, but it's not a good idea. That's why they tell you when you lift things that you should lift with your legs, not with your back, like that old guy is doing. Because the erector spinae is already exerting such large forces because of that small angle that if you add extra forces to them, it can sometimes cause, injury. So you should not lift with your erector spinae. It's possible to do so, but you should not. What did the fish say when he ran into the concrete wall? Damn. All right. Friction is a force that what? Is it perpendicular in the same direction or opposes the direction of the motion? All right, we'll stop at 35, 35. It opposes the direction. So say, for example, I have an object and I'm pulling it across the floor. The frictional force will always oppose that direction. Remember, this is our kinetic frictional force. It always opposes the direction of motion. That's why in the Aristotelian view that we think that things are always at rest, because the frictional force, if I have something moving, the frictional force causes it to stop. It always opposes that direction of motion.
So in other words, it goes opposite direction.
Right, opposite. Yeah, in the opposite direction.
So then which one is perpendicular?
Perpendicular is the normal force. Yeah, be careful, keep those in your mind. Remember the normal force, like if I push against the wall pushes back on me. Or anybody ever been in a fist fight? Good demonstration of normal forces. If you hit somebody in the face, I'm not saying you should get in a fist fight, but if you hit somebody in the face, then their face, like, literally punches your fist back with a normal force. You should think about it that way. Has anybody ever been in a fist fight? Yeah. Mm-hmm. Because of fist fights?
Yeah.
I think that fist fights used to be more common. I think that people are fist fighting less now.
That's too much work.
Yeah. All right. Yeah, really. All right, show me the center of mass for this wedge of wood. Is the center of mass at point A, B, C, or D? I'm sorry, I was looking for my little, I have this little bird with a center of mass outside of the bird. I'll look for it next time and bring it next time. But here, where is the center of mass? Or the center of gravity is the same. All right, let's stop at 27, just a few more seconds. Oh, very good. C is right. The center of mass is not at the very center. The center of mass is to the right of there because you have more mass down at that edge. Kind of like with the meter stick when I had the mass down here, the center of mass was actually right about here. It's like a wedge, right. All right. Why do cows make great scientists? They're like almost always great scientists. You don't know why?
Maleficent?
Hmm?
Like Maleficent from Maleficent?
No, that's not it at all.
I think mine was better than yours.
No, we're not laughing. We're not laughing with you. No, they're always outstanding in their fields. See, my punchline was better, was it not?
Mine was way better.
It was interesting. All right, let's.
That was the thought she put into
She puts some thought into that. All right, let's try this very last one, then we'll move on to chapter 2. You want to draw a picture. I find drawing a picture helps a lot. All right, doing pretty well. Feel free to ask your neighbor if you want. Listen, the problems on the test, they won't be that hard. They'll be a lot like these. They'll be hard if you don't know the material. If you haven't read the book, haven't been going over the notes. But if you know the material, it'll be an easy test. Like, you'll be in and out. But if you don't know it, it's going to be hard. Okay? That's true for everything, right? It's hard if you don't know how to do it. All right, let's stop it. We'll stop at 107. All right, C is right. 1 meter from the fulcrum. It helps to draw a picture. and it didn't help that much. I have a 50-pound kid down here. 50-pound kid is 2 meters from the fulcrum, 50 pounds. And so the torque due to this is 100 pound meters. And then I want to know, where do I put a 100-pound kid? Like, where does the mom go? All right, she's going to go here. I know that she has to be closer of 100 pounds. Just from experience, that if we want to seesaw with a little kid, we have to sit closer to the fulcrum. But I want to know actually what is this distance. I'll call it R. And so I say 50 times 2 is equal to 100 times R. 50 times 2 is 100, so R is equal to 1 meter. 1 meter from the fulcrum. You'll have to do some torque problems that'll be similar to that. You'll probably also have to do a torque problem like we did before, where instead of just having one force over here, I'll have 2 forces. Like with the bicep problem with the dumbbell. We have the dumbbell, the weight of the forearm, and the force of the bicep. Okay? What's that?
I said, I'll see what I've got it wrong.
Okay. Practice, practice, practice. Even if you feel like you know how to do these, like in class when you're sort of sitting here and we're talking about them, it might seem easy. But you'll really know when you sit down and work through an old exam and then see how you do. So that's sort of your homework for tonight, is that you print out an old exam and you just take the exam and see how you do. If you make 100% on it, you probably don't even need to study. But if you make a 70% on it, you need to go back and read the chapter, read through the notes, practice some of those old exams again. There's enough there for you to practice 3 or 4 times. All right. Any lingering issues from chapter 1? Okay. We're going to move on to chapter 2 then. If you have questions, we can come back next time if you have some burning issues next time. All right. So this is sort of a hodgepodge of different things. Pressure is a force per unit area. The definition for pressure mathematically is P is equal to F divided by A. Let me just make a point here that from here on, or at least in this chapter, when I write pressure, or a capital P, I'll write it with a little base on it. The reason is that we're going to see the Greek letter rho, which looks a lot like a P, and so I'm going to use my P will have a base on the bottom just to help you distinguish the two. Pressure is required to move a fluid. Anytime I want to have a fluid move from one spot to another, I have to exert a pressure, a force per unit area. So for example, we'll see this come up. Breathing, we need to have a pressure applied. Blood flow, your heart applies pressure. Digestion, that third class of muscles, remember we had the skeletal muscles, the cardiac muscles, and what was the third one? The smooth muscles. They're used to move fluids through the bodies. And then also delivering medicine. We have a section on drug delivery at the end of the chapter. That's like, giving drugs to people, not like delivering drugs, illegal drugs from one point to another. Okay? So we're not talking about that kind of like drug running, but administering medicines to people. Okay? Is that clear? Good. The units of pressure are the Pascal. This is the abbreviation for the Pascal is PA. By the way, when you have units, it's just a little FYI, that when you have units, if it's named after a person, when you write out the unit, you don't capitalize it, like the Pascal or the Newton. But when you do the abbreviation for it, you do capitalize it. That's why some units are capitalized, because they're named after a person. This is also equivalent to, in the SI system, of 1 Newton per square meter. And then I also just want to remind you, oh, wait, no, I'm sorry. There are some other units for pressure that you might be familiar with. There's inches of mercury. There is millimeters of mercury. You're probably most familiar with that. That's what they measure blood pressure in. Millimeters of mercury. Or you might have heard it in terms of atmospheric pressure. That 1 atmosphere is 760, I think, millimeters of mercury. We'll see where that comes from. That you actually get a physical column of mercury, actual mercury, that corresponds to those pressures. You also see atmospheres. This is abbreviated ATM. What's that, Kate?
760
Millimeters of mercury. Yeah. As I said, we'll see that again later, where that comes from. You see the bar, which is a measure of atmospheres, and then you can also see centimeters of water, H2O. Those are just some different units that we have for pressure. We'll see them as we go through the chapter, mainly in the sense that we'll see sort of where these distance and material, these three, where those three come from, because they're all related. They have to do with a particular device called a manometer or a barometer, and how that works. I also want to remind you of your area, because area is important, because it is force per unit area. And so just to remind you that area in general is length times width. So if I have a rectangle, it's the length times the width to find that area. If I have a circle of radius r, the area is pi r squared. So force per unit area is my my pressure. Steven, let me see your hand. Let's flip it around. Does that hurt? Good. Does that hurt? Good. Because look, I have a fairly blunt end on this. Does that hurt? Good. A little bit. I feel the point. I can feel the point. The point is that that I get a bigger pressure when I use the sharp end. Why do I get a bigger pressure when I use the sharp end? Okay, because it's more focused in that area. What else? How else can you say it?
The force is greater.
The force is greater. No, the force, I'm still applying the same force.
Like same force in a smaller amount of area.
Right, the same force, but in a smaller amount of area. So if I decrease the area here, that increases P. So if the area goes down, that means that my pressure will go up. If I make the area smaller, the pressure goes up. I'd like to show this. I always use this one we have like prospective chemistry students. This is a balloon. Have you ever thought of a balloon, like the remarkable nature of a balloon and the way that it's changed your life? Those people that design balloons, right? They make them. We didn't used to have balloons. In fact, y'all ever read Little House on the Prairie books? Who's read those? My daughter likes them. Y'all read them? Remember the part where Laura gets a bladder from her dad? Like he was slaughtering the pig, and he takes the bladder out of the pig and he gives it to Laura. Y'all remember that book? You don't remember? Okay. But he gives her a bladder, and he fills it up with air. He blows it up with air and ties it off just like a balloon. And it just reminds me that back in the 1800s, they didn't have balloons. They didn't have plastics like this. And plastics are pretty remarkable because they're airtight. See how they're airtight? They can hold a liquid or a fluid or a gas. And then they're also just really strong. They're flexible. You can put them inside of your body and use them for certain things, like to correct problems in your body. And then also, I like this about balloons. I can take the pointy end, and put it here. And look, it seals around. Y'all see the thing in there? Look, it's self-sealing. It's leaking a little bit. But these materials are self-sealing. Like they stretch around the object that goes into it. How does, yeah? I hardly ever pop them. Isn't that remarkable? Have you ever thought about a balloon and how much it's changed your life? Like, they're not just for parties. They are very remarkable material. That's what chemists do, right? They make materials like this. In fact, we have a faculty in the department. He's making new organic molecules that you can use for optoelectronics. You know what that means? That organic molecules are molecules like what make up your body, carbon molecules. And optoelectronics are like your cell phone. And your cell phone right now is made up of mostly silicon-based materials, the electronics in them. But if you can use organic-based materials, then you can actually print out and create materials that are very flexible. So you could take your big old clunky cell phone, see it's a new one, it looks kind of nice, right? It's a nice cell phone. But in 10, 20 years, it's going to be one that you can roll up and stick in your pocket. Or you can create these paints, organic optoelectronic paints, and paint a wall, and then it becomes a monitor.
What?
Yes!
I've heard
Isn't that crazy? I mean, they already have them where you paint a wall, and then you can apply electric voltage to it, and it illuminates. So you don't have these fixtures, you just paint the ceiling, and the whole ceiling is illuminated. Anyway, he's doing that too. Yeah.
Trying microchips to be like in your hand. That's what I thought too.
Right.
I was waiting for it too. I was like, when he puts that thing in there, it's gonna pop.
Anyway, the point of that is that your pressure is a lot bigger when I have the small pointy tip. Alright? Because that area gets smaller. There are 3 possible sources of pressure in a fluid. Your book talks about this. Taylor. What did I say?
Yeah.
Oh, if the area, about the area and the pressure, if the area goes down, it gets smaller, the force increases, or excuse me, the pressure, the force stays the same, the pressure increases. I said it mathematically like this. P is F over A. If the area decreases, that means the pressure increases. We'll see those types of relationships later. That's called an inverse relationship, where if one thing goes up, the other thing goes down.
Inversely proportional.
Inversely proportional, as opposed to directly proportional. And a direct proportionality, we also have one here, is if the force goes up, the pressure goes up. All right, so 3 possible sources of pressure in a fluid. The first is the weight of the fluid. Right now, you are sitting under the immense pressure of a fluid. Are you aware of that? That you have this fluid that's pushing down onto your body. You have roughly a kilometer or more of fluid that's sitting right on top of you and just pushing down into your body. You know, ever do any diving?
Yes.
Yeah? So what happens as you go deeper and deeper and deeper?
It hurts.
Yeah, the pressure increases. In fact, you don't have to be a diver. You can just go down to the 5 or 6 foot end of a pool, and you can feel the pressure that's pushing it on you.
Jumping into the water and going down like 10 feet, man, that's painful.
Yes, yes. I have a video I can show you.
I was doing that with my son during the summer at the pool over here, and I could feel my ears just like crushing. You wouldn't go down that far.
So we have this fluid that is pressing in and around that bottle as you go deeper and deeper. Kayla? What? Oh, I don't know.
Yeah, that's
It looked
Well,
like
he must be. He can't go 70 feet.
yeah, that's what I was wondering.
Although I have a
All the
friend,
buddies are-
maybe so. I know a guy. He's not the world record holder, but he's pretty darn close to the world record holder for free diving. and he can stay under for about 5 minutes with no gear.
Oh.
And I don't know the depth that he can go, but he does. They have a rope, and you basically just pull yourself down as deep as you can.
What
And
is the world record?
it's a little bit more than him. He actually trains with the lady.
So if that would have been full of water.
If it would have been full of water, it would have kept its shape. Because water, we'll talk about that later, is incompressible. But air, on the other hand, is compressible. So you can take a bottle that's filled with air and compress it.
Wait, if water is incompressible, what happens in space whenever it forms into little circle things? Is it not being compressed?
No, it's incompressible.
That's crazy.
That's crazy, isn't it? All right. A few more minutes. All right. The second thing is you can have external force applied to the fluid. We'll see this. We'll talk about it in more depth, but this is like in hydraulic systems. We'll see that if I apply a force on one part of a hydraulic system, I'll see it throughout that entire system. And then also the internal force of the fluid. These are the three ways to have pressure in a fluid. The internal force due to the interaction of molecules. All right. So first, the weight of the fluid. What is it, Kate?
Sorry.
That noise is our.
That noise.
It's our vent hood. We have the big gray things on the top of the building. This is a lab building mostly, so the ventilation is different from other buildings. But sometimes when it's really humid and wet outside, the bearings squeak like that. It needs to be greased, I think. Yeah. All right, so atmospheric pressure results from the weight of the fluid at sea level. We can derive the pressure, like the actual pressure that we experience. If we think about a column of fluid, now when I say fluid, by the way, I mean anything that can flow. So that means a liquid, which is usually what you think of as a fluid, or a gas. So a fluid is a term that includes both liquids and gases. Anything that can flow. That's where the word comes from, fluid, flow. So I'm talking about liquids or gases. So I consider a column of fluid that's over a particular point. Let's think about our bottle. You know, I'm in a container filled with water, a lake in that case, and I have some object that is a certain depth below the water surface. It's at a depth I'll call H. So it's a depth H, and the area, it has a surface area that I'll call A. Now, there's a column of liquid that sits on top of that block. And you can think of that column of liquid literally as like it's sitting on top of it, like a 700-pound gorilla. It's sitting on top of it, and it's pushing down on the bottle. And that's literally what causes the bottle to collapse. Think of it, it has this bottle, and then on top of it, there's this big column of water that's pushing down on the bottle and causing it to collapse.
Would there be an example of a vector?
Yeah, that's a vector, like a force vector. Sure. Now, the liquid has a density rho. It has a density, and we call that density rho. This is the Greek letter rho, lowercase rho. We use it for density. You've seen density before, I'm sure, in high school or middle school even. Density is a mass per unit volume. So some things are more dense than others. gases are really not very dense at all. Metals are more dense. Wood, for example, is another solid. Is it more or less dense than, say, metals, most metals? It's less dense because it has less mass per unit volume. So liquid has a density rho. The weight of that fluid, the weight of this fluid right here, is equal to the mass of the fluid times the acceleration due to gravity. And that's going to be equal to the density times the volume times the acceleration due to gravity. We're just doing a little derivation here. We'll get to something in just a second. Notice the mass is density times volume. Now, pressure, it's force over area. That's going to be density times volume times G. That's the force, divided by the area. But if I take volume and divide it by area, I'm left with just one unit of length. So we're going to simplify this as just rho times G times H. And that is our expression for pressure. You'll need to use it. It's on your equation sheet, and you'll have it for the exam come next Tuesday. But just be familiar with it. They talk about it in the book, and we'll talk about it more next time. Okay.
So rho is mass divided by volume?
Yeah, rho is mass divided by volume. That's the definition of density.
The way you wrote it kind of makes me think of the other
Oh, mu?
Yeah.
Yeah, that's not an M, that's a mu. But yeah. Alrighty, you folks have a good day. Like I said, if we do cancel class on Thursday, we'll just bump everything back a day, okay?
Oh, before we close out,